Good morning. My name is Paul Zignoni from LinkedIn. I'm a network engineer there. On our network engineering team, we run a handful of large data centers, a global backbone, and a number of edge POPs around the world to make sure that our 450 million members can connect to LinkedIn. Today I'm going to be talking about some of our experiences that we had in a recent 25 gig deployment in the data centers. So about a year ago, we had a new design. It was going to be all 40 gig base switch or inter-switch links in our new data center design. And before last year, 25 gig didn't really have any practical options, at least for us. But about late 2015, 25 gig seemed to be extremely viable, both in switch and optics options out there. Why do I say that 25, 50, 100 gig is the new 10, 40 gig? The prices have come down. There's a lot of competition already. So that's been very helpful for us. There's multiple switch and optics options out there, and as well as cabling. So whether you're looking at twin-X cables and the standard fiber options that you can connect to your switches. 25 gig on the optic side had a number of short-range and long-range options that will become relevant later in the presentation, where you see some of the distances that we had to work with in the data center. Divide by 4. So when you're talking 25 or 100 gig, it looks a lot like 10 to 40 gig. You can get to keep a lot of your same switch over subscription ratios. And 25 gig, a lot of the hardware out there, the electrical side is already at 25 gigs, so it makes for really efficient transmission out to your fiber. And then finally, a lot of standards had been finalized around 25 gig, so that gave us the comfort to move forward with it. So in terms of optics, what is out there for 100 gig? So everybody should be familiar with 40 gig QSFP plus modules. The 100 gig QSFP 28 modules look exactly the same SFF spec, or it's a different SFF spec, but it's the same size to go in your switch. So just like 40 gig, you have the same copper options. So like on the top row, you'll find your CR4 based options. These are twin-X or pre-molded copper-based cables. It's 4 lanes of 25 gig carried over copper in a pre-molded cable. Second row down, you'll see in turquoise, those are your multi-mode based options. So SR4, 40 gig SR4 is one of the most popular out there. 100 gig SR4, we're not sure if that's going to become the most popular, but it's available and it works exactly the same way. It's 4 physically split lanes across a set of 4 fibers for transmit, 4 fibers for receive. Finally, on the single mode options, LR4 has been a spec around for 40 gig. It's a spec around for 100 gig as well. It has, by the spec, a reach of 10 kilometers. It can be a very hot optic to reach that, but it allows you 100, or on the 40 gig side, 40 gig over a single duplex pair of single mode, and the lanes are wave division split to get you that 100 gig. And then finally, at the bottom, on the 100 gig side, there's an option out there, PSM4, that actually looks a lot like SR4 in that it's the lanes are split across different fibers instead of different wavelengths on the same fiber. There are some vendor-specific implementations of that on the 40 gig side, but on the 100 gig side, PSM4 is an option that we actually decided to pursue, and I'll get to those reasons in the following slides. I should mention that there are a couple other standards out there that you might find for the data center. I wrote on the slide that they might be useful in your data center, but actually they may not, just because as things are moving forward, everything's becoming more and more 25 gig based. 25 gig based to reach 100 gig, that is. And one other thing before I proceed, I should point out that I mentioned 50 gig quite a bit in this presentation because of the way that we ended up using the PSM4 optic, but also there are new standards coming out that around 50 gig, where 50 gig is actually the transmission. So that's not actually what is covered in my presentation, but if that's of interest to you, definitely be on the lookout for that. So anytime that you're going to consider new pluggable in your environment, a few things to keep in mind. Temperatures and power. A 32 gig or 32 port switch filled up with LR4 optics so that you can send that many ports down 10 kilometers sounds really great, but not all switches are going to actually be able to provide you that much power and temperature density. So keep that in mind and make sure you check your specs. Also on density. It's very easy when you're looking at the increased density of a switch, how many ports you can load up and how many cables. But the last thing you want to do is plan your data center with 6-inch wire managers between cabinets, which might seem really generous when you're talking about a bunch of duplex fiber, but then you realize, oh, the CR4 cables might actually be a lot cheaper, and you order those, but before you know it, you've loaded up your wire managers with more cable bulk than they can handle. The cables might be spilling out, and under the weight of them, pulling the wire manager off the cabinets, and you've made enemies with your data center staff in the meantime. That's something you want to avoid. The distance to your patch. So there's the overall distance spec by whatever optic you're going to use, but it's important to keep in mind how far is the actual patch panel from the gear that you're going to be locating. This is especially important if you're going to be using breakout cables, because the expense of them can be significant, and you want to make sure you're getting the lengths right. Finally, any legacy gear or any other legacy requirements that you might have where you might be building in new pluggables. Even in our case where we had a brand new data center to light up, we still had some specific gear that had, like appliances that had specific attachment requirements that didn't exactly fit with all the fiber cabling that we were planning. And on the topic of density, you can see how quickly density can become an issue, even with a half-loaded 32-port switch with CR4, in this case, CR4 breakout cables. Another really important consideration, whether it's a new optic of a new spec or a new optic of just a new vendor and you're going to be plugging it into existing gear, is interoperability. So definitely testing is important here. Case in point, when we did testing on the new optics for our new build, we had 3 different options from suppliers to test. They all each individually tested to each other just fine until we started to interconnect them between the vendors. We didn't find that kind of problem when we were testing 40 gig optics when we introduced those into our data center, but of course those standards are a bit more mature. So anytime you're doing something bleeding edge, you need to make sure that you're paying attention to testing a lot more. So I'm going to go over a bit about our deployment experience with PSM4, but first I'm going to review some of the design requirements that we had at LinkedIn on this new data center. So first we had a distance requirement over 100 meters, and that was, we had all of our network gear was going to be stationed in 2 different core rooms, and then we had 1 large data hall for all of our server cabinets. We also had expansion plans, which are actually now in effect, of a new data center building across the parking lot. So hence the 1 kilometer requirement as well. We had a 32 port QSFP switch figured out initially in our 40 gig design. We kept that sizing, obviously a different switch when we decided to go to 25 gig, but we had already planned on making use of more than the 32 physical ports on board by breaking them out into different logical ports. The other couple requirements, we wanted to make sure that we built with single mode. Obviously the distance that we were looking at required single mode, but we also wanted to make sure that we were able to have a build in place to take advantage of wave divided lanes for future builds that might exceed 100 gigs. And finally, in the initial design, it was 4 by 40 to reach 160 gig connectivity from our top racks upstream. Obviously, if we go to 4x20 to 4x50, and then we're able to achieve that with a little bit more. So what did it look like? What we ended up doing was the PSM4 optic. First of all, it was a cost-effective way for us to leverage the single mode fiber requirement that we started to build into our data center. In fact, 2 of the PSM4 optics give us a little bit more bandwidth than the 4 40 gig optics. And in fact, at a lower price than what we were seeing on the 40 gig world. So what we did was we proceeded with a top rack switch with only just 2 PSM4 optics. But then what we did was we had to channelize 2 of the 25 gig lanes from each PSM4 into a logical 50 gig optic. So I should also call out, if you decide to take this upon yourself, that the cost that you might get between your switch, your optics, your cables, and the length of your cables based on your data center install might change that formula. So I'm definitely speaking from what was cost effective for us. A couple things about PSM4, just for if you haven't heard about it. It looks a lot like an SR4 optic in that it uses an MPO connector. You attach to it with an MTP cable. It's got 12 fibers there. Just like SR4, it's exactly the same thing. You have the 4 transmit on the left, lanes or fibers 1 through 4 for lanes 1 through 4, and then on the right, receive fibers for lanes 4 through 1. So a simple rollover will be able to connect those two. A rollover MTP patch cable if you're going to go back to back between 2 optics. Another quick thing to review. Now these as network engineers, this you might actually be very familiar with, right? A straight through cable is pretty basic. A rollover cable, pretty basic. Flipped pairs kind of cables, so anytime that you have multiple fibers, or even in the copper world, you're going to find that. But what we might not know, and I didn't know a year ago, was that in the cabling industry, these are actually referred to as methods A, B, and C. Those are the specifications out there for that. Handy to know when you're talking to somebody in the cabling industry about this stuff. Okay, so on to our patching challenge. So as I mentioned, we had 2 core rooms, core network rooms, and all of our spine switches and fabric switches. So spine is kind of the middle tier of our fabric. The fab switches are at the top tier, and at the bottom, as is on the bottom on this slide, is our top of rack switch. So as I mentioned, there's 2 PSM4 optics in each top of rack switch, and then the 2 50 gig bundles that we get from each PSM4 optic, we want split between the 2 core rooms. This is extremely advantageous in terms of redundancy and failure scenarios, but it does make for a cabling challenge. So what was our solution? Solution was from top rack to spine switch, and first of all, I apologize if the details are too small, but you're welcome to download these off the NANOG site in the PDF that's up there. In any case, what we did was breakout cables from each PSM4 optic in the top rack switch to LC ports in the patch panel local to the server cab, connected via an MTP trunk to a panel in a very large distribution row of distribution panels in the center of the data hall. From there, it was all LC jumpers to additional distribution panels in that same center patch row. And from there, MTP trunks split between the 2 different core rooms. So the split of those bundles basically happened in that distribution row with those LC jumpers. And then in the core room, we have patch panels located relatively close to our spine switches, or CSWs as we call them here. And from there, breakout cables that go to PSM4 optics in the spine switches. I should point out the whole design of top of rack to spine switch to fabric switch, we architected around being able to use the same switch or the same switch spec, basically a 32-port QSFP single chip switch, and all around the same optic. And in this case, it turned out to be PSM4. So a second cabling challenge. from the spine switches up to the fabric switches, and this is a lot more dense cabling. It happens to be all in the same room, but we did have them separated. So in this diagram, you'll find on the top a very simplified view of spine to a fabric topology. But when you consider that those sets of switches are going to be separated by patch panels, there becomes a certain cabling pattern that you can work around. And so if you look at the lower picture, you'll see if you kind of pinch those cables, and considering that they're going to be connected to a PSM4 on one end of an MTP trunk, then what you find is that you have a particular opportunity to use it looks more like a Y cable rather than a full breakout. So I introduced the LinkedIn Y cable, and what this does is basically gives us MTP ports on either end of that Y cable. So first, for a lot of us out there, if you're thinking, that's interesting, I didn't know that you could design your own cable and have it manufactured. And then maybe there's a few of us that have gone through that process, and you go, yeah, that's actually possible. That's not a bad idea. And if it's me about 10 months ago, you might be thinking, Y cable, why in the world would we do that? It's complicated, and it is, but it works out. And how does it do that? Basically, for all the patch panels in those core rooms that connect between the spine switches and the fabric switches, we locate them immediately adjacent to those switches. So here's a picture of how that turned out. In the upper right, you find the SFP connection, so the trunk side of the MTP of the Y cable, and those fan out. So there's 4 of them right now pictured in that switch, and they fan out to 8 MTP ports on the patch panel below. So we're using all the lanes on the PSM4 side, but only half the lanes in those connectors on the bottom. So these were our plans. This is how we move forward. And then a few things that we learned as we went along, even past our testing. So PSM4 optic, as just like an SR4 optic, it has 4 physical fiber lanes that it transmits on. But depending on your switch platform, as in the one on top, there's only 1 indicator light per optic. So guess what? As we were bringing things up, and on the network side, we get a record of all the links that didn't come up in this new build. We were working with our data center staff on site. And network guy says, I don't see light on this lane or this lane. And data center guy says, well, I see a link light. So that was one cycle that we had to go through to make sure that we understood we really have to look at things on the console and make sure that our data center staff can look at things on the console if we want to enable them to troubleshoot as well. On the other hand, one other switch platform that we deployed on the bottom, they're not lit up right now, but they do actually have positions for 4 lights per QSFP 28 port. That makes it a lot handier, especially if you're going to be breaking out to a full 4 by 25 rather than bundling it the way that we did. Another consideration for PSM4, and pretty much any new optic that you might find, the switches recognized the optics just fine, and they worked. But when we were troubleshooting individual lanes within a bundle, the switch only saw the first lane. That lane was good, but then we had to go and troubleshoot the second one. So that was just a software thing that needed to be able to recognize all the lanes in a given bundle. And we were able to make that work. As soon as we reported it to our vendor, there was basically a bug fix already available. So that wasn't too much of a headache, but a demonstration of the little bumps in the road you can get. Another consideration, if you're rolling out a data center and you're using ZTP, especially on the front panel ports, how does your switch know what ports, or how that port's going to be configured when he's sending the DHCP request to basically ZTP himself? So in this case, you've got the way that we cabled up the PSM ports. Some switches will, when they do their ZTP or bootstrapping method, will actually try different combinations of link on something like a QSFP port. It'll try it as a native 40 or 100 gig. It'll try it as broken out 25 gig. But I haven't seen anybody that looks at it and says, oh, somebody must intend for this to be a pair of 50 gigs. So in our case, we kind of foresaw this one issue, as well as a few other reasons that we ended up using the out-of-band management port on all of our switches. Final consideration I'd like to point out is what's your capacity impact. So PSM4 really worked out for us in terms of being cost effective, being able to use just 2 ports to get the upstream bandwidth we needed. But mind you, it's only 2 optics, and so half of your bandwidth, or half of your upstream capacity relies on a single optic. So this changes a little bit the ECMP scenario where if you lose one link or one component that you lose 25% of your capacity, and what we've changed this here is that you end up losing half of that. So it looks more like a redundancy scenario. It's definitely a risk we were willing to take, but if it's something that you're considering, definitely keep in mind all of those different failure scenarios and how that can affect your capacity. So, summary of our experience and exploration into 25 gig. First of all, 25 gig is here. It's definitely viable. It's economical in many ways, and we see pricing across the board getting closer and closer to the 40 gig world that we were living in before. PSM4 is a less talked about standard out there, but it is out there. It was available for us, and we made good use of it. Definitely check for platform availability. There's a couple different options out there in terms of what switch forwarding engines will actually work natively at 25 gig. So again, a couple years ago, that was really limited. Today, it's definitely available. You don't have to be a really large data center operator to be able to take advantage of it, and it's there. So a few lessons for us, and hopefully for all. If this is your first deep dive into a single mode data center, so for single mode for all of your intra-switch cabling inside the data center, definitely review best practices. One of the best practices that we found most important is making sure that you're polishing all the ends of your fibers. So as you unpack your fibers, and before inserting it into the plug, make sure you're polishing them. On the multi-mode side, or in the multi-mode world, you can definitely get away without doing that, just because there's a lot more tolerance on the multi-mode side for that. Definitely not on single mode. Budgeting time for design and testing, can't say this enough. You're going to go through several cycles anytime that you're introducing a new design, even if it seems as simple as a new optic in an existing topology. Finally, testing your optics, testing your cables, doing your interoperability testing, and performance testing as well, which I didn't cover in here, but performance testing for us didn't reveal any issues. And finally, plan all your cable routing. So if you're somebody that does networking and data center planning, then you're probably already in good shape. If you have a larger team where you have network engineers and data center engineers, I can't stress enough how friendly you need to be with those people and make sure that both sides understand the designs. A few references I'd like to make. Obviously, there are the consortiums around the standards for some of these new technologies. I'd like to point out the NANOG at the beginning of the year. I enjoyed a presentation from Christian Ukariat from Finisar. If you're interested in 25 gig, that particular presentation has a lot more detail available on a lot of those optics and a lot more roadmap discussion, which might be useful. So with that, I'll say thank you, and I've left quite a bit of time for questions if anybody has any.
Hi there, Colin Corbett with Twitch. I had a couple of questions. Where did you put the flip in the A to B, I guess would be a good question. Did you decide you do it at the end? Did you do it in the MTP backhaul, or just questions like that?
Sure. You mean basically where did you roll the cables to make
Yes.
sure that you're, yes. So that was done in the cabling infrastructure itself. So here you have, you can't do it twice, right? On the
Right.
Otherwise, you're going to end up with a straight side. We did it on just one of those MTP trunks.
And then as you hold it back to your distribution, you're doing it in the, you're dealing with it there as well. Or as you're...
So the breakouts are effectively straight, but from within all those pairs, you just need to flip once. And so that's done within the MTP trunk.
Okay, and I guess since you're only doing that within the rack, you didn't have to deal with the male or female or any sort of like extended backhaul as you're going, you know, back to your core or anything like that. It seems like your cables are just female to female at that point.
No, so all the ports that pop out of the patch panels, those are going to be all the female sides. All the cables themselves, they have the male end. So you can flip on either side, right? But if you flip just once on the, in this case on the MTP trunk, when you flip on the MTP trunk, then you don't have to worry about where else to flip. So that makes the breakouts a lot easier. Obviously, there's more complexity in the breakouts. As for the connectors, the standard follow there is female connectors on all the patch panels. The patch cords, so those Y cables, have all the male ends. Obviously, on the client side, on the PSM4 port, that's the female end there.
Cool. Thank you very much.
Yeah, thanks.
Hi, Christian Ricari from Finisar. Nice presentation. Thank you for the reference at the end. You mentioned this custom cable that you made, the LinkedIn Y cable. Is that a cable that's widely available, or can be purchased by anyone that wants to implement this architecture? You know?
So that cable, it's a proprietary build or design by us. We're looking at potentially sharing that. We would definitely like to hear if people have more interest in that. There's one gentleman from our team that was actually very key in designing that. Brad, he's here today. So definitely you can talk to me or to Brad as well if you'd like to find out more about that process or more about the actual design.
Thank you.
Thank you.
You are from Yahoo. So one question, can you comment on the decision of making 4 planes instead of 2 planes? Because with the PSM4, if you just make 2 planes, then you don't have to deal with all the Y cables and the 50 gigs, and we're maintaining the same oversubscription ratio.
Sure. So you're asking about the number of planes set up by the number of switches at the different layers?
Yeah, so what I see from there is that you could actually just make 2 planes instead of 4 and still maintain the same oversubscription ratio, and also to avoid making the Y cables and basically cabling at the 50.
Sure. Thank you. Yeah, that's definitely true. But even before we made the decision to go to these speeds, having those 4 planes from the top rack up to the spine layer has always been part of our design. What we like about that is that it allows us to use relatively simple single switch or single chip switches where we can tolerate a failure of one, and it's not that we're losing redundancy, but we're only losing that 25%. Obviously, that model is broken if we're losing an optic, but it's more predictable that we're going to need to reboot switches. Right, so having a 4-way ECMP at different layers of our network allows us to have that predictability of capacity, when we either need to do maintenance or when we in fact do lose a switch. So, but definitely a good question. Thanks.